Welcome students to this lecture of wireless communication. So today we will study automatic repeat request. So automatic repeat request, this is basically a mechanism used in data link control and transport protocols. So in the communication networks lecture, you remember you studied about these different protocols and you had this transport layer and data link layers there. So automatic repeat request is a mechanism associated with the data link and transport protocols. So these mechanism relies on use of an error detection code that can be any error detection code, for example cyclic redundancy check or any other forward error correction code. And automatic repeat request involves flow control as well as error control. So so let's see, let's assume that you have a source and a destination and you are transmitting this PDU. So PDU, they stand for protocol data units. Okay, so basically these are the actual messages that are divided into different packets as you would normally do for a packet switching system, and then there are different additional headers and frames added together to those packets, and then they form this protocol data units. So these PDUs, they are transmitted, and let's assume that there is no error between the source and the destination. So this is a model of an error-free PDU transmission. So each PDU starts from the source, and after a certain time delay it reaches the destination. So had there been no time delay, this would have been received at this point, but since there is a delay in the transmission, the delay is actually denoted by this gap. So that's why these slanted arrows are shown here to denote complete transmission of this PDU from source to destination. So and all these PDUs are experiencing the same delay. So that's why all these lines are parallel. Okay, let's say if PDU2 had a higher delay, then it would have been, let's say, reached like this. Okay, so the delay is same for all the PDUs, and then they reach the destination after that certain delay. So this is a time diagram to show the transmission of PDUs. Okay, and this is an error-free model. If there were errors in between or let's say further delays experienced, then these lines will not be parallel to each other. Okay, so let's now assume that we have a system where your flow control mechanism works. So in such a scenario, what are the different assumptions? So for flow control, it assures that the transmitting entity does not overwhelm a receiving entity with data. Okay, so that's the first assurance of flow control. Then the protocols that employ this flow control mechanism, they allow multiple PDUs in transit at the same time, and the PDUs arrive in same order that they are sent, and then you have a sliding window flow control. Okay, so what does that mean? This means that the transmitter maintains a list of sequence numbers allowed to be sent. Okay, and receiver maintains a list allowed to receive. Okay, so let's say the transmitter can send, let's say, 5 PDUs at a time, and let's say the receiver can receive 5 PDUs. Let's assume that the transmitter and the receiver has the same rate of transmission and reception. So 5 PDUs can be transmitted and 5 PDUs can be received, let's say. So the transmitter maintains a list of sequence numbers allowed to be sent. So let's say it maintains a list which says that PDUs 0, PDU 1 up to PDU 4 can be sent, and the receiver also maintains this list that PDU 0 to PDU 4 can be received. So you can see that basically this means that the transmitter maintains a kind of a window that gives the numbers or sequence numbers of these PDUs. So it can maintain a window of 0, 1, 2, 3 and 4. Similarly, the receiver can maintain the same window. And as these numbers change, the window is adjusted. Okay, so that is what is meant by sliding window flow control mechanism. So this example that I just showed you says 5 PDUs in the transmitter and 5 in the receiver, but this may not be the same. Maybe the transmitter is fast and it can send 5 PDUs, but the receiver, let's say, is slow and it can only receive, let's say, 3 PDUs. So this can also be done. So the window size in the transmitter and the receiver can be different also. So so let's see this example. So you have this sequence number of PDUs 0, 1, 2, 3, 4, 5, 6, 7, etc. So there are 8 PDUs that, let's say, a transmitter has already transmitted. Okay, and and let's say the 0 to 5, okay, has been already received. So let's say this 5 is the last PDU that is acknowledged. Okay, and 6, 7, these are the PDUs which are buffered but are still not acknowledged. Okay, so and 7 is the number of the last PDU that is transmitted. So you see you have transmitted 0 to 7. 7 is the number of last PDU that is transmitted, but 5 is the number that was last acknowledged by the receiver. Okay, so out of 0 to 7, 0 to 5 has been confirmedly received by the receiver. So in that case, your transmitter maintains a window that can be transmitted whose length is 5. Okay, so since 5 is the sequence number of the last PDU acknowledged, your your window size is 5. So you have already sent 0 to 7, so your window starts from 0 again, and since 5 up to 5 is the number that has been already confirmed by the receiver through this acknowledgement, you can send 5 more starting from 0. So that's the window size that is maintained in the transmitter. Okay. Now the window shrinks from the trailing edge as PDUs are sent. Okay, so let's say right now the window size is this. Now if you send this PDU, then the window size shrinks to this. Okay, if you send this PDU 1, then the window size shrinks to here. And similarly, the window expands from leading edge as acknowledgements are received. So if the receiver now sends you acknowledgement of this, then this the window increases again. Okay, so again, if the receiver sends acknowledgement of, let's say, PDU 6, then the window expands again. So the same thing happens in the receiver side also. Here also the window shrinks as the PDUs are received, and the window expands as acknowledgements are sent. So window expands means you can now receive more PDUs. Okay, because you have sent an acknowledgement, you are now ready to receive more PDUs, so your window can increase. Okay, the window shrinks means that you have already received these PDUs and your window size decreases. Okay, so this is how this sliding window protocol operates. So as you send more, the sender's window shrinks, and as you get more acknowledgement, the sender's window expands. From the receiver side, as you receive more, your window shrinks, and as you acknowledge more, your window expands. So that's the sliding window protocol for you. So now let's see an example of a sliding window protocol. So let's say you have two systems, A and B. So A is your source and B is your destination. So for both, let's say we have an initial window size of 7. So between 0 to 6, the initial window size is 7 for both the transmitter and the receiver. Okay. So now let's assume that the source sends 3 PDUs, P0, P1 and P2. Okay. So now what happens is that as the sender or the source sends P0, P1, P2, its window size shrinks from 7 to 4. Okay, since it has sent these 3 PDUs. Okay. In the receiver also, the window size shrinks, okay, as it receives these 3. Okay, so from 7 it shrinks to 4. Now let's say the receiver, after receiving all these 3, sends an acknowledgement RR3. Okay, so RR3 means receive ready 3. So RR is a kind of acknowledgement which is part of this ARQ mechanism. So if you are actually receiving some packets, then you send this acknowledgement, which is a positive acknowledgement that the packets have been received. So you can see that the last PDU received was P2. So the receiver will send RR3. Okay, so since this is 2, it will send an acknowledgement which has the next number. So if the last PDU received is I, okay, then the receiver sends RRI plus 1. Okay, so this is the way of telling the transmitter that all the PDUs up to I has been successfully received. So P0, P1, P2, all of them are successfully received. So that's why the receiver is sending RR3. And the moment it sends RR3, its window expands to 3 places. So earlier it was here, 4, and now it expands to 3 places because it has successfully received 3 PDUs and it has room for receiving 3 more PDUs. So the window expands to 3 places. And when the transmitter receives this acknowledgement, which is RR3, it knows that 3 of the PDUs that I sent earlier has been successfully received by the receiver, so I can send 3 more. Okay, so the transmitter now knows that it can send 3 more new PDUs along with the 4 that was before. So the window size now again expands to 7. Okay, so now let's say the transmitter again receives sends P3, P4, P5 and P6. Okay, so these 4 PDUs are sent by the transmitter. Okay, and the receiver receives, let's say, a P3 only, and the moment it receives P3, it sends out the acknowledgement RR4. Okay, so therefore the window size now expands to 1 place here and decreases 1 place here. Okay, so it was initialized at this point, so this decreases 1 place because it receives P3 successfully, and since it sends out RR4 after receiving P3, it increases 1 place to this. Okay, so now let's see what happens. So now after the RR4 has been received by the transmitter knows that after the transmitter sent out P3, P4, P5 and P6, the transmitter window shrinks to this. Okay, and here what happens, let's see. So after the P3 was received, it already sent RR4. So this was the stage that we had. Now let's say these 3 also are eventually received, so therefore the window size now again shrinks 3 more places and it's now here. And in the transmitter side, after it receives this RR4, it knows that it can send 1 more PDU, so it increases to 2. Okay, so this is the final state. So transmitter stays at 7012, the window size of 4, and the receiver stays at 7012 of window size 4. So after the receiver has received this P4, P5, P6, if it sends out, let's say, RR7, then the window size will be shrunk to 3 places. The window size will increase to 3 places like this. Okay, so this is how this whole sliding window protocol works. So the reasons for breaking up a block of data before transmitting is because of the fact that the receiver has a limited buffer size, okay, and retransmission of PDU due to error requires smaller amounts of data to be transmitted. So this is important on a shared medium because larger PDUs occupy medium for extended period, and this can cause delays at other sending stations, okay. So therefore it is important to break up a block of data into smaller PDUs before transmitting. So now we saw flow control. Now let's move to error control. So error control is a set of mechanisms to detect and correct the transmission errors. So there can be two types of errors. One is a lost PDU, so a PDU fails to arrive from the transmitter to the receiver, or it can be a damaged PDU. So this means the PDU arrives, but a lot of bits in that PDU are in error, okay. So this is the scenario here. So you saw this is the error-free scenario, which is like PDU, all PDUs are received at a certain fixed time delay, and this is the scenario where you have losses and errors. So here your PDU2 may not arrive at the destination at all, or there can be some errors in a PDU. For example, PDU4 is received but with a garbled frame, okay. So in such scenarios, what happens is that you detect the error. So the receiver detects errors and discards the PDUs. But if there is no error, then the receiver sends a positive acknowledgement, okay. So it returns an acknowledgement of received error-free PDUs to the transmitter, okay. And then there can be negative acknowledgement also. So if there is an error or there is a lost PDU, then the destination returns a negative acknowledgement to PDUs in error, okay, and it asks the source to retransmit, okay. So the source will retransmit this PDU which was in error, okay. And the final case is retransmission after timeout. So if there is no acknowledgement of a PDU, okay, so unacknowledged PDU, there is no acknowledgement whatsoever, let's say, from the receiver, either positive or negative, then in that case also the source retransmits the PDU, okay. So the source retransmits the PDU in two scenarios: one when there is a negative acknowledgement and when there is no acknowledgement. When there is no acknowledgement, the source waits for a certain time, and after the time is over or a timeout happens, then only it retransmits the PDU. So based on these, there are different ARQ mechanisms. One popular one is called go back N ARQ. So in go back N ARQ, you can have two types of acknowledgements. One is called RR, which we discussed a few slides ago. This means receive ready, and this also denotes that no errors have occurred. So this means this is a positive acknowledgement. And REJ means reject or error detected. So this is a negative acknowledgement, okay. And then different contingencies can happen. One is a damaged PDU, okay. So the PDU itself is damaged, but then there can be a damaged RR or a damaged reject, okay. And based on these different conditions or different contingencies, you can have different scenarios. Okay, so let's consider the scenario 1, which is damaged PDU. Okay, so if the received PDU is invalid, let's say you have the sender A and the receiver B. So if the received PDU is invalid, then B detects an error and B discards the PDU, of course, and takes no further action as the result of that PDU. Now, under this case, there can be two subcases. Okay, so let's say within a reasonable period, A subsequently sends PDU I plus 1. Okay, so let's say my PDU I is in error. Okay, and B rejects, discards this PDU. Okay, and within a reasonable period, A subsequently sends PDU I plus 1, which is the next PDU. B receives PDU I plus 1 out of order and sends a reject I. Okay, so B received this PDU with error. Okay, now it discards this PDU, and then after a certain time A sends the next PDU, but B is waiting for this one. Okay, so when B gets the next PDU, it doesn't receive it. Okay, it sends a reject I. Okay, and when this reject I is received by A must retransmit PDU I and all other subsequent PDUs. Okay, so let's say your A, okay, has sent PDU 5 to B, and then this is in error. So B discards this PDU 5, and then after some time A tries to send PDU 6. Okay, B will not receive this PDU 6. Okay, B will not receive it. B will send a reject 6 to A, and when A receives reject 6, A will know that something was wrong with PDU 5. Okay, so it will now resend PDU 5 and then PDU 6. Right. So A must retransmit PDU I and all subsequent PDUs. So this is subcase A. Now subcase B can be that A does not soon send additional PDUs. Okay, and B also receives nothing and returns neither a positive acknowledgement or a negative acknowledgement. Okay, and then in the meantime A's timer expires. Okay, so when A's timer expires, it transmits an RR PDU that includes a bit known as the P bit, which is set to 1. Okay, so B interprets this RR PDU with a P bit of 1 as a command that must be acknowledged by sending an RR indicating the next PDU that it expects, which is PDU I. Okay, so let's imagine this case again. So PDU, so let's say this is A and this is B. Okay, so A had sent PDU 5. Okay, let's say PDU 5 was sent, and this was in error. So A sends B does nothing. We are talking about subcase B here. So B does nothing. B waits it sends neither an RR nor a reject, and A also sits quiet. A also does not soon send any additional PDUs. So in the meantime, let's say A has waited up to this point and A's timer expires. So timer expires means A will start resending PDUs, but at this point when the timer expires, A knows that it had sent a PDU 5 before the expiry of the timer, whose acknowledgement has not been sent, and the reason the acknowledgement is not sent is because it was received by B in error. Okay. So, so after the timeout, A sends an RR to B, and this RR has a P bit which is set to 1. Okay. And when this happens and B receives this RR, B interprets this as a command that must be acknowledged, and it acknowledges this by sending an RR to A, and this RR indicates the next PDU that it expects. So this RR will be RR 4, okay, because the next PDU it expects is 5. So moment the A receives this RR, it will start sending PDU 5 again to B, okay, and all other subsequent PDUs, PDU 6, 7, whatever. So so this is what happens when a PDU is damaged. So there can be two subcases, okay. One is that A sends out the subsequent PDUs, but B won't receive that. B will say, okay, I am rejecting it because I haven't received the previous PDU, I am waiting for that. Or it might happen that A is not sending anything and its timer expires. B is also idle because it received a damaged PDU. So after the timer expires, A will send a RR with a P bit which is set to 1. Once B receives this RR with a P bit set to 1, it will immediately acknowledge that, sending an RR that indicates which PDU it is expecting from A. And when A receives that RR, it retransmits the PDU I, which in our example is PDU 5. Okay. So now there can be the second case where an RR is damaged, and for that also you can have two subcases. Okay. So let's say B receives PDU I and sends RR I plus 1, which suffers an error in transit. So because acknowledgements are cumulative, that is RR 6 means that all PDUs through 5 are acknowledged. It may be that A will receive a subsequent RR to a subsequent PDU, and that it will arrive before the timer associated with PDU I expires. So let's say this is your A and B, okay. So let's take the example of PDU 5. So PDU 5 is sent by A and it is received by B, and B sends out a RR which is 6, saying that it has received all PDUs up to 5, okay. So so RR 6 means that all PDUs up to 5 has been successfully received, okay. So now let's say this RR suffers an error in transit, okay, and A, when doesn't receive this RR, but let's say A sends PDU 6, okay, to B, and if it receives an RR 7 because of this successful reception, then A knows that all PDUs up to 6 has been successfully received by B. So it doesn't matter that RR6 or any other RR which was sent by B was damaged in transit, okay. So if it receives RR7, it knows that RR6, up to RR6 everything else has been successfully received. So that includes PDU5 also, okay. So you don't have to receive this RR6 due to PDU5's successful reception, okay. So and if this RR7 arrives within the timer expiry of A, okay, then it is well and good, okay. So there is no damage done here for this subcase A. For subcase B, let's say if A's timer expires and it transmits an RR command same as case 1B, so it sends an RR command with a P bit, and that P bit is set to 1, and if B fails to respond to the RR command, or if its response suffers an error in transit, then A's P bit timer will expire. At this point, A will try again by issuing a new RR command and restarting the P bit timer. So so let's say if A's timer expires, then A will send RR with a P bit, okay, similar to case 1B. Now this P bit also has a time, okay. So if that timer also expires, okay, and it still doesn't receive B's response because B's response gets damaged again, then this P bit timer is restarted, okay, and this process is repeated again and again for several iterations. After several maximum number of attempts, if A fails to obtain an acknowledgement, then it initiates a reset procedure, so everything will start over again, okay. So so this is the scenario when you have damaged RR, and the damaged reject, this process is equivalent to case 1B. If a reject is lost, so this is equivalent to case 1B, where again A will wait until its timer expires, and then it will send an RR with a P bit, and then you will have the same case as case 1B, okay. So so if you are confused with this part, then I would actually strongly encourage you to go through this part in the textbook written by Stallings that I have recommended you for this module, okay. So let's move on. So this is the entire timing diagram that also you can look and see the explanation that is there on the slides or in the book, and then you can relate what is happening for the different cases of damaged PDU damaged RR or damaged REJ. Okay, and then you can be able to appreciate what exactly is happening for these particular three cases of go back and ARQ. So so now let's move to hybrid ARQ or HARQ. So as you saw from the previous example, when you are doing ARQ may create excessive delays, okay, because of retransmission. Okay, so if you go back, see the process of ARQs, there are some timer associated. So A is waiting for its timer to expire. If it expires, then it performs some operations again. For example, A tries this procedure several iterations, and then it waits for a maximum number of attempts, and then if still it fails, it initiates a reset. So you see there are a lot of delay associated with the ARQ process. So you are sending something, if that is received with no errors, you are fine, but if there are errors, then you have lot of retransmissions, lot of waiting, and that may cause excessive delays because of the retransmissions. And then when you are using forward error correction, so forward error correction means as you saw in your previous lectures, basically it corrects the error, not only detects. So in case of ARQ, what happens, it detects the error and then there are retransmissions. For forward error correction, it corrects the errors also. Okay, so you can either use, let's say, forward error correction, or you can use ARQ, let's say. So either you have a mechanism to completely correct the errors, or you have a mechanism where you detect the errors and you allow retransmissions. But then neither FEC nor ARQ is adequate in practical situations, because ARQ will cause excessive delays and FEC may add lot of unnecessary redundancy. Okay, so that's why HARQ is widely used, which is a hybrid between ARQ and FEC. So it uses combination of FEC and ARQ. Okay, so so there are different HARQ approaches. We can have soft decision decoding, we can have chase combining, and we can also have incremental redundancy. Okay, so let's see what is soft decision decoding. Okay, so let's compare soft versus hard decision decoding. So let's say you have your messages which are 2 bits. So you have input bit 1 and input bit 2. So these are the 2 bits of your messages, and you are adding a parity bit. So your code words are 3 bits. So for message bit 00, you have a code word 000. For 01, you have 011, and so on. Okay, so now you are transmitting the message, let's say 01. Okay, and you are sending it through this parity encoder that adds another 1 here. So you are sending 011 corresponding to 01 through your channel. Okay, and at the receiver you are doing a hard decision decoding. Okay, so when you are doing hard decision decoding, basically you are measuring the levels of the received signal at certain sampling instance, and you are comparing it with a threshold. Okay, so let's say your received signal gets degraded by noise and other impairments in the channel, and it looks like this. Now if you set your threshold to 0.5, then and if these are your sampling instance, then According to hard decision output, this is 0, okay, because this is below the threshold. This is the sampling instant for the next bit, so this is also 0 because it's still below the threshold, and this part is 1, okay. So you receive a 001 after hard decision, okay. Now 001, when it is passed through the decoder, basically the decoder checks the Hamming distance of the hard decision output with the original code words, okay. And Hamming distance is nothing but in how many places the bits vary. So the Hamming distance between 001 to 000 is 1 because only these bits is varying. With 011 it is again 1, with 101 it is 1, and with 110 it is 3. So the idea is the output of the hard decision is compared with the other code words in terms of the Hamming distance, and whichever gives you the lowest Hamming distance, you decide that that particular code word was transmitted. But here you can see there is a tie between these three, so you are confused which one was actually transmitted, okay. So this is avoided in case of a soft decision decoding. In case of a soft decision decoding, instead of comparing the sampling instant values with a hard threshold, you just take the absolute values of these points. So let's say this is my sampling instant and my absolute value is 0.2 volt here. In the next one I have 0.4 volt, and in the third one I have 0.7 volt, okay. So now if you if you calculate the Euclidean distance between these voltage levels, instead of let's say taking the Hamming distance, so the valid code words are these. So 000 means 0 volt, 0 volt, 0 volt, and 011 means 0 volt, 1 volt, 1 volt, etc. And these are your voltage levels at each sampling instant of the received waveform. So now you calculate the Euclidean distance. So Euclidean distance between 000 and the received waveform is simply 0 minus this value square plus 0 minus this value square, and so on. So this is how you are calculating the Euclidean distance, and this gives you 0.69 as the Euclidean distance between the received waveform sampled at these instants with the code word 000. Similarly, you do the Euclidean distance with the other code words and you find that this one is the minimum, and this means that there is a chance that this particular code word was transmitted, and which is indeed the case, that this one was transmitted, and therefore the message 01 was transmitted. You can easily decode that. So you can see that with soft decision decoding you have an advantage compared to hard decision decoding. The chances of errors are much less in case of soft decision decoding. So, so when you are doing HARQ, you can have chase combining and incremental redundancy. So in case of chase combining, you can retransmit. So if there is an error, you can retransmit the same data plus parity bits combinations for all of the 4 retransmissions, okay. And the receiver keeps all the transmissions. So let's say you are doing transmission 1 and there is an error, but it doesn't discard the transmitted frame here. It keeps it. Then you do the next transmission, the same thing is repeated, and after the 4 transmissions you combine everything together using this MRC technique, which is called maximum ratio combining, to get back the original information. In case of incremental redundancy, every time you try different things. So in transmission 1 you do some combination of coded bits, okay. If there is an error, you do a retransmission. In the next transmission you just increase the redundancy a little bit, okay, to see how it works. And you can have different combination of codes in different retransmissions, and then in the receiver you can see which one gives you less error or no error, okay, and then you can find out the original information from them. If you want to learn more about this, then I would encourage you to go to this website. So here you have this website which is called rfwirelessworld.com, and you can read about chase combining and incremental redundancy in more detail here, okay. So this is the website, rfwirelessworld-world. So there are additional approaches of hybrid ARQ like puncturing, then parallel HARQ, etc. So okay, I will stop here today, and I will start wireless LAN in the next video lecture. So I'll stop here today. Thank you very much.